Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. In this lecture, we would discuss about histogram based image enhancements in the spatial domain. This lecture will be more of a introductory level about histograms, and the next two subsequent video lectures we would go in more detail about methods like histogram equalization and local histogram equalization. I'm sure you all know by this time what a histogram means. We could say it as a progress report of the intensities present in a given image. More formally, you could think of it as an abstract representation of intensities present in a given image. So for example, take the image that is there on the left hand side. Assume that a data type used for representing the image values at each pixel is 8 bits, that means unsigned char. So you will have intensities from 0 to 255, and then what this histogram would give you is on the x-axis you have the possible intensity values that a pixel can take, and on the y-axis you have number of pixels that are having this particular value of intensity. So in other words, it tells you the distribution of intensities in a given image. As I mentioned just now, this is like a progress report of the intensities that are there in a given image. It would be helpful if you could in fact expect the nature of the image just by looking at the histogram, and also being able to tell how the histogram would be by just looking at the image. Take the histogram here. So what can you say here? Again, assume you have a set of intensities from, let's say, 0 to 255. That's clearly telling you that you have intensities somewhere around the 200 100 to 255, which means you could say about that image that the contrast in that particular image is less and the image intensities are on the brighter side. That's what you could interpret from this histogram. Let's see how its corresponding image would look like. As we have rightly analyzed, this image is on the bright side and the contrast is somewhat limited and somewhere from the middle value to the highest intensity value. Here is another histogram for you. What can we infer from here? You could see here the contrast. By contrast we mean the distribution of intensities. That's very less here, right? So the distinctions that you could see in terms of intensities would be very cramped or very close to each other. Let us see which is the image that is being represented by this histogram, right? You could see the same in this image. Here comes another image where you could clearly see that it is well distributed across the whole range of intensity values. From the histogram, it looks like this image should be having a reasonably good contrast. Let us see how it looks like. Again, this is in line with our observation. Here is the slide where we are putting all those histograms and the corresponding images in one place, as we have rightly inferred. For example, this is a dark image as the distributions are limited and they are on the low intensity side. This is on the high intensity side, but still this is a light image. It's not well spread as such. While the first one is a dark image, you could say from the histogram that this is a light image. And here is an image where it is neither dark nor light, but it's of low contrast image, the distribution being very narrow. And this is the image where you could say that it's of high contrast image, as there is an even distribution, almost even distribution of intensities in the histogram. From this, you could already guess that in order to have a good high contrast image, what you would expect is to have a even or roughly even distribution of intensities in the histogram. So that's what in the next class and the class after that also we would be looking at methods that operate on the histogram of a given image and redistribute these intensities in such a way that you could get a better contrast image, or in other words an enhanced version of the original image. There are various applications of histogram. For example, one we have already seen right now is analysis of the image. Just by looking at the histogram as we did just now, you will be able to say whether it's a dark image or a bright image or a low contrast image or high contrast image. Another one is you could use this histogram for increasing the brightness also in some cases, particularly when the intensity distributions you see are concentrated over the dark region or on the left hand side of your histogram. Here is an example for illustrating this. We will see Einstein in almost all these examples. You could notice here that there is a gap here, right? So there are no intensities on the high end. Let's say from maybe some last 50 intensity values are not present. So in that case, once you could see it from the histogram, all you could do is simple shift of intensity. So you go through each pixel, assume that the highest intensity in a given image is 200. Then what you could do to make the image bright is that you could simply add, let's say your highest being 200, whereas you could go up to 255. You simply add to each intensity a value of 55. That would make your image bright. This could be one special case where histogram can be used for increasing the brightness, and this way of shifting is also referred to as histogram sliding. The other applications being image equalization, we will come to that in the next class, and also we would extend that discussion in the class after that. Another application could be you could use it in thresholding. In the last class we already had some discussion about what it means by thresholding. Suppose you want to get your object of interest. Assume the cases where your object of interest is having a distinct distribution of intensities separate from the rest of the image. In such cases, in order to get your object of interest either segmented or in order to enhance that, you could use histogram information. There are few other ways a histogram can be used, and we are going to see a couple of more examples in this class. You could think of histogram stretching as a generalization in a way of what we have seen as histogram sliding. Now consider the case, particularly the case where your intensities are concentrated around just one region. So that's equivalent to an image with a low contrast. Now what you could do is you could in fact spread it across the whole image. Assume that you have an image in which the distribution of intensities are between 50 to 100. Now this 50 could in fact go to 0, this 100 could go to 255, and then you could distribute all the rest of the intensities proportionately. So that's what this histogram stretching does. This is a quite easy one to understand. In the specific example that we have considered, fmin is 50 and fmax is 100. What this is going to do is wherever when this f of xy is 50, that's going to map to 0. And now from every intensity, since you are subtracting fmin, that means this would be, for example, which was earlier 100 would now get subtracted from 50. Okay, that becomes 50, and again fmax minus fmin is 50. So this highest intensity is now getting mapped to 1. The intensities which were earlier equal to 50 and 100, they got now mapped to 0 and 1, and this getting multiplied with the largest intensity value that you could have in the image. BPP is bits per pixel that you are using to represent the intensities. So in case of an 8-bit integer, this is 2 power 8 minus 1 equal to 255. So you are essentially multiplying it with 255. So when it is 0, this constant is going to be 0. That means this g of xy, the transformed image, will be 0. When this is 1, which would be the case when this f of xy equal to f max, that would now get mapped to 255, and the intensities that are there in between f min and f max will be proportionately moved. A similar example here, suppose an 8-bit data type, minimum intensity being 0, maximum intensity being 225. So what would happen now? F of xy minus, assume that already there are 0 intensities in your image, so this would remain f of xy in the numerator, and in the denominator, if the earlier image is just 225, this gets divided by 225, giving you for the maximum, when f of xy is maximum, this is going to be 1, and since you are multiplying it with 255, that gets mapped to 255. Here is an example of it. Once you apply this transformation, you could see how this got distributed over the entire image. The resulting image, you could see an improved contrast. Anyways, since this image has already a reasonably good distribution of intensities, you won't see a very drastic improvement here. But if you look into the other examples that we have seen earlier, where the contrast is very low, you would see a very high improvement in the quality of the image. Okay, this is a very short video. I made it very short because I wanted to discuss histogram equalization exclusively in one video. So that's what we will do in the next video lecture. Thanks for watching. See you in the next video lecture. Bye. Take care.